Hello, everyone. Welcome to Coffee with Caleffi. We've got a very big topic today. I think this is going to end up being the highest number of registrations that we've had so far for the year. So I think that we hit a nerve with this topic. We're going to be talking about air to slab heat pump systems. Our guest speaker is John Siegenthaler. I'll run through a couple introduction slides, then I'll turn it over to John to take us through the rest of the presentation. So if you're having troubles with audio, there is a tech support number. Generally, just logging out and logging back in is probably the best way to go. If you want to copy the presentation after the webinar's over, hit yes in the survey. We'll send you a PDF of that. And then you can also go back and listen to any of the Coffee with Caleffis over the last 12 years, 13 years, I think, on our YouTube channel there. Then if you are looking for a certificate of attendance, we'll send this out to you as well after the webinar. Then it's got the details that in some jurisdictions you can self-report the credential hours. And so we have an exciting announcement. We haven't updated the video yet, but we took the plumbing category win at the AHR Innovation Award for the upcoming show in February in Atlanta for our Prescal HP. So this is our piston style pressure reducing valve. And we were happy to kind of keep the streak alive of plumbing products. That I believe is our sixth innovation award in the plumbing category that we've either been a finalist or a winner. So we're pretty excited about that. And we'll have more training about that product upcoming as well. This is not the most recent Hydronics, second most recent, but probably most applicable to the class today. So this is Hydronics for low energy and net zero buildings, available as a PDF or on hydronics.caleffi.com as kind of an interactive version of this issue, but really a good one for making the most out of every calorie of energy in a building. And then I think on the next slide, that's the website for hydronics.caleffi.com. You can pull up all the back issues there, either as PDFs or as the interactive version. For next month, we're going to do kind of a take on a class that we did earlier in COVID that we called Shop Talk Showdown, where the three trainers, Bob, Cody, and myself, are going to be talking about air and dirt separation and magnetic separation. And then we also have a couple of things that we usually have kind of a shop talk style argument about. We'll do kind of a live debate of should you leave the autofill open or should you close it? So tune in next month for that. And then that brings us to today. We'll bring John Siegenthaler in to take us through the rest of the slides. And yeah, the topic again is air to slab heat pump systems. Take it away, John.
Well, thanks, Max. Glad to be with you folks. I know we've got a good sized audience today, and it's kind of a niche topic, but it's an interesting topic because it brings together the concept of high mass radiant floor heating and contemporary air to water heat pumps, which we've talked about in past seminars, as well as some previous issues of hydronics. So we're going to look at these systems. We're going to start off with a typical air to water heat pump system, kind of a residential class system. And as you'll see, if we're going to do zoning, we're going to need a buffer tank. And of course, buffer tanks do add complexity. They do add expense to a system, but they are necessary in some circumstances. However, the air to slab topic is really kind of fostered out of this idea: when can I not require a buffer tank in a system? When can I use the mass of the slab itself to stabilize the operation of the system? And that's where we're bringing together what I call a minimally zoned slab-on-grade building, along with an air to water heat pump. And I'll show you a quick comparison between thermal mass just to give you some feel for how much energy storage is possible in a, let's say, a typical Midas muffler shop, as an example, a slab-on-grade building with nominal dimensions. It's fairly easy to calculate it. You'll see it's equivalent to a very high amount of water, several thousand gallons of water, and it's just not practical from a cost or space standpoint to try to use that much water for thermal storage. We're going to talk also about constant circulation in these types of buildings. It's a concept that's been around for a long time. I feel it applies very well in garage type buildings where you have these large overhead doors like you see down at the bottom of the screen there. Those are the areas that cool off faster when flow stops. And they tend to be cool spots, and in extreme conditions, they can also be areas that will potentially freeze. If it's extremely cold and there's no flow and it's just water in the circuit, that's where freezing is going to start. So we're going to mix in constant circulation to the discussion. And then we're going to look at what I'd call kind of a futuristic spin on this topic, where we're going to add additional thermal mass beyond just a concrete slab. And that sets the potential for things like real-time electrical pricing, time of use rates, peak shaving, and many of the up-and-coming techniques that utilities are going to use to try to manage their peak loads. And we'll also talk a bit about some of the control concepts. Basically, the controls on these systems are very simple off-the-shelf controls. So with that, let's start with a residential application. Here's a really simple system. It involves what is called a monoblock air-to-water heat pump. That's a self-contained factory charge unit that would sit outside the building. And you'll see the piping down here that comes into a buffer tank. And in the past, as well as in Hydronics, we've talked about different piping configurations for these buffer tanks. This would be called a 3-pipe buffer tank configuration. And from the buffer tank, you'll see here's a small variable speed pressure regulated circulator. There's dozens of products on the market from all the major manufacturers for that. And then over on the right, panel radiators on home run circuits. Now, this system design, just the way it's shown, there's many zones. And I'm showing a few panel radiators, but you could easily have 10 or 12 panel radiators. And what we don't want to do is create a situation where one panel radiator is calling for heat, and we're turning on a heat pump that has a heating output perhaps 10 times greater than what that panel radiator requires. That's why the buffer tank is there. Okay, we have to stabilize the rate of heat production with the rate of heat transfer to the load. All right. Now, I've taken that system and I've varied a little bit on this slide. This uses a split system air-to-water heat pump. And I'm doing this just to show you two different flavors of air-to-water heat pumps. The monoblock being a factory charge, everything is outside type of configuration. A split system is where we have an outdoor unit with a refrigerant line set that comes into an indoor unit. You can see the indoor unit down here on the wall. The nice thing about a split system is there's no water outside, so you're not required to put antifreeze in the system. The other thing I've added here is cooling, and we will talk about how can we add cooling in some of these commercial structures. It can be very simple, but you'll see there's a diverter valve here that basically takes the output from the heat pump, sends it to the buffer tank in the heating mode, or sends it to the coil in the air handler in the cooling mode. And again, over on the right side of the buffer tank, instead of internal coils for domestic water heating, we've got an external heat exchanger with a flow switch and a circulator. We've got a mixture of panel radiators and radiant floor circuits, all of which are individually controlled as independent zones using thermostatic valves, either valves that are built into the radiator or external valves that are connected to a dial with a capillary tube. So there's many, many different flavors or configurations of systems that we can build around air-to-water heat pumps. And we talk about that a lot in that issue number 30 of Hydronics, as well as number 27. We show several different configurations. But again, I'm showing this as a starting point around residential, and then we're going to switch into this type of building. And you think about the building market, what is out there from residential right up to large commercial. There are a lot of structures that fall into a category of slab-on-grade with minimal amounts of zoning requirements. We don't have 10 rooms in a house, for example, all of which perhaps might be on individual zones. So think about fire stations, highway service garages, shops at a farm where they work on equipment, woodworking shops, welding shops, even aircraft hangars. There's a lot of buildings that fall into this category. where a slab-on-grade floor is a given. And of course, that sets the stage for floor heating. And then, traditionally, in years past, these would have boilers as heat sources. So with the push towards electrification and decarbonization, we started looking at how can we take this niche of buildings and move them over to heat pumps. And the fact that they have a slab floor and would be good candidates for floor heating, how can we bring in air to water, as well as, I should mention, pretty much everything that I'm going to describe around air to water would also work with a water to water geothermal system. So the same or very similar system configurations. The reason I picked air to water in this is if you have existing buildings, you know, in many cases don't have the opportunity to install a geothermal system without, extensive disruption of the facility or the grounds around the facility. So this is that niche of buildings that we're kind of identifying. And what are these characteristics we want to put together? Well, a bare concrete slab, and any of you that have worked with floor heating know that a bare slab has one of the lowest water temperature requirements of any different radiant floor heating system compared to, for example, a plate system where the plates are installed above the floor or below the floor, or a thin slab system on a wooden floor. So as building envelopes get tighter, the water temperature requirements go down. So we're looking for these bare slab types of buildings. Minimal zoning, and I say that because, again, we don't want to take a large slab, especially in a large open area, and just break it up into a lot of zones. There's really no gain in doing something like that. Now, we might have, I put down here below the thermostat, 1 or 2 zones. You may have a major shop area in a building and perhaps a smaller area that might be a break room, maybe offices, bathroom facilities, that type of thing. So I don't want to say just single zone, but minimal zoning where we aren't taking that mass and breaking it up into a lot of little independently controlled elements. Again, we're going to bring air to water heat pumps in, not only as our primary heat source, but also as potential to produce chilled water and add cooling. And many of these buildings, at least in the northern climates, many of these buildings in the past don't have cooling. And it's a nice upsell, especially with bringing the air to water heat pump in. You have the ability to do this. You're in effect buying a chiller when you buy an air to water heat pump. It's just a matter of how do I detail out the distribution system to use that chill water. And I should say from the outset, we're not talking in this session about using chilled water in the floor. Radiant cooling is a specialty subject. It's possible, but let's take it in baby steps, so to speak. We're going to show you how to do it with an air handler, where the condensation issue that has to be very carefully designed in a radiant cooling situation is not there. And as I say, possible interest in cooling. And another really nice feature or benefit of this approach in areas that have time of use electric rates. And I just put down there in the lower right an example of time of use rates. And you can see during the evening and the overnight hours, in this case, the rate was 8.3 cents per kilowatt hour. During the peak demand period there in yellow, it jumped up to almost 13 cents a kilowatt hour. So how could we coordinate the operation of the heat pump with the high thermal storage ability of the slab and with these rate structures? And there isn't one definitive answer on that. Simulation would be one of the ways to predict performance, but conceptually, a high thermal mass slab, or what I call extended thermal mass, could avail of these time of use rates and ultimately draw as much electricity at minimal cost as possible, and certainly bring down the operating cost of the project. So we're going to have 3 poll questions today. The first one, and I'll read it, and I'm going to let Max run the poll. What percentage of your radiant projects would be considered as light commercial or industrial slab-on-grade buildings?
Okay, that poll is open, so I'll leave it open for about a minute, and then I'll read the results just in case you can't see those when they come in, Siggy. And one of the things that we had a ton of pre-submitted questions about radiant cooling. As you mentioned, it is kind of a niche thing. There's a lot of upside for it. We do have a full hour webinar about radiant cooling to kind of best identify the projects that would be a good fit for that. And there may be some overlap with what we're talking about here today, but it's better to kind of go through all those details to make sure that it's a good fit for your building, which we have covered in the past. If anybody's looking for that info, I can drop it into the chat and send you the YouTube link as well. Okay, so let's close the poll here. And then, okay, so 47% of the respondents said up to 10%, 29% up to 25%, and then 24% said 50% of the projects or more. So a pretty good split there.
Yeah, but encouraging though that 24% indicating half or more of their projects would fall in this category. So this concept is potentially applicable to quite a range of buildings. Okay, I will keep moving here. Now, real briefly, any heat pump, the performance of a heat pump is a moving target. It's very dependent on the temperature of the source material as well as the temperature of the material to which you're imparting the heat. So with an air-to-water heat pump, we're extracting heat from outside air. So if you look at this graph, you'll see outside air temperatures here on the bottom, and then heating capacity. And this I believe was a nominal 4-ton air-to-water heat pump. And the thing you'll see, of course, is that as it gets warmer out, the performance of the heat pump improves quite a bit. The heating capacity goes up pretty fast. But the other thing I want you to see is the 3 different curves. Those are for 3 different water temperatures leaving the heat pump. So this would be the temperature of the water coming out of the heat pump and going off to the load. Excuse me. And you can see that the blue curve, 95-degree leaving water temperatures, is definitely the higher performance. So we want to do what we can to keep the water temperatures as low as possible in terms of improving the heating capacity of the heat pump. And it's actually the same story with coefficient of performance, the efficiency of the heat pump, the ratio of the output divided by the input. We want to keep that as high as possible. And again, low water temperatures improve performance. So a bare concrete slab sets the stage for relatively low water temperatures. And just to give you a feel, I worked out one scenario here. If we had a 6-inch slab, 12-inch tube spacing, and we're trying to get 25 BTUs per hour per square foot off the top of that slab, going into a space at 65 degrees. And I picked 65 because many of these commercial fabrication buildings, garages, and so forth, people are working at a higher activity level. Typically, they don't want the temperature to be 68 or 70 degrees. They consider that too warm. Highway garages, we've seen them run anywhere from maybe 55 to 65 degrees because the people have more clothing on, or as I say, they're working at a higher activity level. So all this would require is an average water temperature of 93 degrees Fahrenheit. And if you consider 25 BTUs per hour per square foot per reasonably insulated building, certainly we can get that load lower with more insulation. You can see we're at bathtub temperature water. We're at down supply water temperatures varying maybe from 98 to a little over 100 degrees at design load, and then we can use outdoor reset control to bring that water temperature even lower. So again, we've got a nice match between the water temperature requirements of that bare slab and the conditions that give good performance on the air-to-water heat pump. Now, let's talk about thermal mass. I just picked arbitrarily a 40 by 80 foot slab-on-grade building with a 6-inch thick slab. We'll just use that as a starting point. The heating capacity or heat capacity of concrete, the number of BTUs it takes to raise a cubic foot of concrete 1 degree Fahrenheit is 29.4. So we just multiply that by the volume of that slab, and you can see we come up with a thermal mass of roughly 47,000 BTUs per degree Fahrenheit. Now, what does that mean? Well, it means it takes roughly 47,000 BTUs to change the average temperature of that slab by 1 degree Fahrenheit. Or another way to say it would be a 1 degree drop in slab temperature would release about 47,000 BTUs per hour. And that's pretty significant. So how does it compare to water? Well, here it is. That particular slab, if we compare it to the heat capacity of water, you need about 5,600 gallons of water to match the thermal storage ability of that slab. And obviously that's a pretty big ask. And just to show you, this is what a 4,000 gallon ASME tank looks like. Typically any tank over 119 gallons most codes are going to require ASME certification. And you can see that these tanks are made, but they're very large, very expensive. I wouldn't wager a guess on the price of that tank in today's economy. So it becomes impractical to try to match the thermal storage ability of that slab with water. And as I say, the slab is there. It's part of the building. You're not paying extra. You are adding cost by putting tubing in the slab and putting insulation under the slab, although the latter might be required by energy codes today. But with minimal additional expense, we're accessing the thermal mass of that concrete slab. Now, I mentioned earlier constant circulation. Here's an example. This is a highway garage, actually where I live. This is a relatively new building, and it's for storing snowplows. You can see we've got some large overhead doors there. And here's a detail, a photo I shot when they were building this. And you can see there's insulation under the slab. You can see the tubing there, but you can also see that there's no insulation here where the slab actually goes out under that overhead door. And that can be a nice benefit because the heat transfer that goes out through that concrete by conduction actually prevents ice from forming under that door and freezing the door down to the slab. And it does melt the snow just a few inches out. But this is the downside of this. Imagine if we had controls on the system and we had a deep thermostat setback at night, water in the tubing, and imagine that it's 15 or 20 below zero out, which is possible where this building is located, and there's no flow going through that circuit for, let's say, 10 hours or 12 hours, it will freeze. So constant circulation, I use the term, it stirs the BTUs within the slab. We have a lot of energy stored in the core area of that slab. And what we want to do is bring some of those BTUs out to the perimeter where these cold spots are, and by doing so, prevent that freezing. So we like constant circulation in these types of buildings because, especially where we have these large overhead doors. Now, it is important with these garage facilities, actually with any building. Today, there are codes, there are ASHRAE standards on ventilation, and they could vary depending on what the building is. But in a garage type building, and I'm using, again, a highway garage, when snowplow like what you see in the lower right comes in, that could have several hundred pounds of snow on it. And it's going to melt, it's going to drip down on that floor. The concept is that the first way we want to deal with that water, if possible, you want it to go down a drain. It takes a lot less energy to get rid of that water if we can drain it away rather than evaporate it. And of course, if we evaporate it, we're putting moisture in the air. We're going to create a fairly humid environment inside. And depending on what the insulation system is in that building, we can create a lot of problems. And we've seen a number of problems over the years with these types of buildings, especially where there's no good continuous vapor barrier on the insulation system. Excuse me. Moisture will move into the insulation. It'll find its dew point, it'll condense, and we've literally seen ceilings where water will drip out of the ceiling and so forth. So One of the ways to deal with this is cross ventilation. And this particular garage, this is the air intake. It's a large louvered panel with a motorized damper on it. And you'll see over here above the truck, a couple fans. These fans in this particular building are just controlled by a timer. And there are speed controls on them so they can vary the speed of the motors. But you can also put a humidistat into a building like this and set it so when the humidity rises to a certain point, the humidistat is just a contact closure that would activate those fans and bring enough fresh air in from the outside to keep that moisture, that humidity under control. So I stress that if you're dealing with any kind of a garage facility, and especially in a cold climate where moisture, snow comes in, you want good drainage, and you definitely want to have some type of moisture control approach. Now, it could be dehumidification, it could be heat recovery ventilation, but oftentimes these garage type projects, oftentimes they don't have the budgets for high-end ventilation systems like heat recovery ventilation. So cross ventilation is more typical. Now, let's jump right to the system configurations here, and bear with me just 1 minute, just want to move something. Go. So here's how simple these systems can be. We'll start with a monoblock heat pump. Remember, that's factory charged. It's outside. So we see some vibration isolation hoses here connected to piping. We're simply coming into a hydraulic separator, like a SEP4 separator. So we have a circulator here that's been sized up for the flow rate requirement of the heat pump, which is typically in a range of about 2 to 3 gallons per minute per ton of heating capacity. So a 4-ton machine might have anywhere from 8 to 12 GPM requirement. And we have a circuit between the hydraulic separator and the heat pump, and we've sized that circulator up for it. Now, on the other side of the separator, we have another circulator just going to this high mass floor system. And I'm just showing a single manifold. It could be multiple manifolds if it's a large facility. You're probably not going to bring all those tubing circuits back to a single manifold, but you may have multiple manifolds. They might all be controlled as a single zone though. And the nice thing about the hydraulic separator is this allows constant circulation on the right side. So we can keep this circulator running 24/7 during the heating season, and we're simply injecting heat. We're monitoring the temperature of the water going into the floor, and I'm showing this going directly back to the heat pump. Some heat pumps can do this. They have internal controls that can be set up for outdoor reset. One of the things I would tell you to check when you're looking at these heat pumps, can they access a what I call a system sensor, a sensor that is outside of the heat pump that could be monitoring the temperature at this location. If you can't do that, the other alternative is to use a separate outdoor reset control that can do that and simply turn the heat pump on and off based on that separate outdoor reset control. So we've got constant circulation in the floor. As that temperature at sensor S2 starts to drop slightly below the target value, and the target value is constantly being calculated by the outdoor reset controller based on the settings as well as the current outdoor temperature. If it sees that temperature dropping slightly below the target, it's going to turn the heat pump on. So we're going to inject heat into our thermal mass. And once that sensor temperature rises perhaps 2 or 3 degrees above the target temperature, the heat pump's going to shut off. So it's a really simple system. There's no need for a buffer tank in there. It allows us to do constant circulation. The separator is giving us not only the hydraulic separation of these two circuits, but it's providing the air, dirt, and magnetic particle separation for us. Very simple. Again, I put a note here, because this is a monoblock heat pump, we're using antifreeze throughout the entire system. Okay. Now, just to show a variation on the idea here, I just changed it to a split system heat pump. Remember, now we have an outdoor unit, we have a refrigerant line set here, an indoor unit, and I've added a boiler. And the boiler can be either an existing boiler or it could be a new boiler. If it is a modulating condensing boiler, there's no need for mixing valves. There's no need for anti-condensation protection. And you can see the boiler is simply piped up in parallel with the indoor portion of the air-to-water heat pump. Each has its own circulator with a check valve. Each has a purging valve. And each just dumps into the hydraulic separator. And again, we can set up for constant circulation over on the right side. Now, how you control these two heat sources, there's a lot of possibilities. The basic one would be let the heat pump be the primary heat source. So that would be fixed lead stage heat input. And the controller would watch the supply temperature going to the floor. If the heat pump is unable to keep the target temperature or the actual measured temperature close to the target, it would bring the boiler on. That's just a typical two-stage heat input controller. There's several of them on the market. But it also opens up the possibility that we could use the heat pump during off-peak hours where we have lower electrical rates, and then we could switch to the boiler during peak time. The other nice thing about the boiler is in utility areas that have demand charges on commercial meters, which is common, you could avoid a high electrical demand that you would have, for example, with an electric boiler by using a fossil fuel boiler. So it can be a peak shaving tool, a demand reduction tool, supplemental heat input if it's very cold out and the heating capacity of the heat pump is not high enough to meet the building load. We have supplemental input. And finally, depending on the size of that boiler, we may have the ability to completely heat the building if the heat pump was down for service. So if we had a failure for whatever reason of the heat pump, we've got a full backup. And we could run that, by the way, on a very small generator. Running a heat pump on a generator is possible, but it's going to have to be a multiple kilowatt generator. And certainly in a larger commercial building, it might require a large stationary generator if we had multiple heat pumps. Whereas a boiler, minimal electrical input requirement. So there are definitely advantages, benefits to a dual fuel approach where we're combining the air-to-water heat pump as our primary heat source and then using a boiler as our backup heat source. Now, I'm sure some of you are wondering, well, how do these air-to-water heat pumps perform in a cold climate in this kind of a setup? Well, last year we worked on a project for New York State Energy Research and Development Authority, NYSERDA, and we developed a pretty detailed software simulation for air-to-water heat pumps with a variety of climate zones. Now, because it was a NYSERDA project, these climate zones are just, at present, are just New York State locations, but they vary from very cold, 8,000 degree days, down to, let's say in Brooklyn, I forgot, 5,500 degree days, something like that. So we've run this simulation, and I ran it for Syracuse, which is kind of dead center in the state. It's about 6,700 degree days. I just took a 1,500 square foot building with a fairly high design load, 30 BTUs per hour per square foot. Assume we're trying to maintain 65 degrees inside and the outdoor design temperature was 0. We put a 4-ton low ambient air-to-water heat pump into the heat source model. The bare slab was assumed to require 105 degree water temperature at design load. We did employ outdoor reset control under partial load conditions. We assumed that we had a 3 kilowatt average internal heat gain from equipment, lights, people. And we definitely included the derating effects of defrost. When any type of air source heat pump in a cold climate has to go through defrost cycles. It's going to build frost under certain atmospheric conditions. We have to defrost that unit. That does require energy. Basically, you're putting the heat pump temporarily into cooling mode, and you're using the hot gas to melt the frost. Well, what we found with these specific inputs, we found the heat pump was supplying 93% of the total seasonal space heating energy, and our average COP, coefficient of performance for the winter, was 2.88. And I was impressed. I think that's a very respectable number. It's starting to approach numbers for geothermal heat pumps. It may not be right, not quite as good, but especially in a retrofit, certainly much lower cost, and even in new construction, definitely lower cost. In an unsubsidized market, the return on investment is definitely better on the air to water than it would be on a geothermal. So it shows you that you're going to get respectable performance in this type of system in a relatively cold winter climate. And you may be thinking, well, gee, what do I do if I have a higher load than maybe a 4 or 5 ton heat pump? Well, there's options. One option is to get into staged single phase heat pumps. And single phase heat pumps go up to about 5 tons. Beyond that, you're into a 3-phase unit. And they do exist. You can buy 20 ton, 50 ton, even 100 ton air to water heat pumps. Several of the big names in the industry are starting to bring out these commercial size air to water heat pumps. And, that's another possibility. But going back to a single phase situation where, again, in rural areas, you may not have 3-phase power available to these facilities, you can do staged heat pumps just like we do staged boilers. So this system shows, the schematic shows 2 heat pumps, independently controlled, each having its own circulator with a check valve. And again, we're just dumping into the left side headers of the SEP4 hydraulic separator. And we maintain constant circulation in our high mass slab over on the other side. We're using off the shelf multiple, oftentimes they're called multiple boiler controls, but multiple heat source controls. The controller really doesn't care if it's a boiler or a heat pump. It's a contact closure as far as the output goes. So the lower left, that actually is a facility down in Massachusetts with 6. And those are, I believe those are each 5-ton units. And I do know of some projects that have done this. And again, the limitation here could be single phase power versus going with a larger heat pump. And you also have capacity control. So with 6 heat pumps, you would have 6 stages of heat input. So the controller could better match the heat pump output with the load. And again, minimizing the need for any kind of thermal storage in the system as far as the buffer tank. Now, we've talked a lot about heating through the slab. What about offering I call it the upsell of cooling? When you buy a heat pump today, just about all the heat pumps, whether they're air to water or water to water heat pumps, just about all of them come standard with reversing valves. And that means you're also getting a chiller. So we can add an air handler and a circuit to on the right side there. And you'll see I've just shown a diverter valve. Now you would have to make sure the flow capacity of that diverter valve is large enough. It's probably going to be larger than a zone valve, depending on what the flow rates are. But if you're dealing with 10 to 12 gallons per minute of flow, you would need a CV up in that range for a reasonably low pressure drop. And you can see the idea. The diverter valve simply sends heated water to the floor slab in winter, and it redirects the chilled water flow to the coil in the air handler. So it's a simple modification, and I like this idea because some of these facilities, at least the facilities that I see more or less in rural areas in upstate New York, many of these shop facilities don't have cooling. They just they turn on fans, they open the doors and the windows. But if you can bring a heat pump into the picture, you have the potential to bring additional business by simply saying, how would you like to do cooling in this building by adding that air handler? Now, again, I always stress, if you're dealing with chilled water, which you would in this system, all the piping and all the piping components that are conveying chilled water must be insulated and vapor sealed. You cannot do a poor job with that. So, excuse me, here's another configuration. All I've done here is use 2 different circulators, one for floor heating and the other for the air handler. The advantage of doing this is that if you have significant differences in flow rates or head losses, you can size each circulator up for the flow and head requirement of its respective circuit, as opposed to a single circulator with a diverter valve. Okay, so that's another option. So let's go to another poll question. We've been talking about cooling, and do you see the potential to upsell chilled water cooling based on having this heat pump in the system in a traditional shop or garage building in your area? So Max, I'll let you run that poll and we'll see what the results are.
Okay, so we've got the poll open, and this one looks like it might be more of a landslide. I'll share those results in a second. I'll keep it up a little bit longer. A lot of questions coming in about where to find more information about the heat pumps that are available in your area. And I know that more are coming onto the market every day, but I would say probably the best generic answer would be to reach out to your manufacturer's rep and see if they know of equipment that's available in the area, and you can find parts for it and all those different things. But it seems like every day more is coming over, and some products that are widely used in Europe and in Asia already.
Yeah, the global market in air-to-water heat pumps is about 4 million units per year. About half of that goes into China. Europe is around 600,000 units. I just saw a statistic for Italy. Last year was 150,000 air-to-water heat pumps. And so air-to-water heat pumps are going strong in these traditional hydronic markets. And what's driving it is the decarbonization directives in Europe.
And I imagine that's going to go fast in Europe this year with the war in Ukraine too. That if people are having issues getting gas where they normally have that, I think that might speed up this whole thing.
Canada is also moving fast towards heat pumps. So yeah, there are at least off the top of my head, at least 7 or 8 manufacturers right now of what I'll say residential scale air-to-water heat pumps, residential light commercial scale. And there are more coming into the market each year. There's some major players that are likely to be in the market. When I say major, global heat pump manufacturers that are, they have been watching this market develop. And I think they're ready to move into the North American market based on, again, many, many programs for decarbonization. So yeah, there's a lot of product out in the market and more coming.
So the results of the poll here, do you see the potential to upsell? 79% said yes. So that I think is a sign that cooling is not so much of a luxury item anymore. So yeah, I'll switch back to the slides.
Good. Okay. Now, I was just talking about the need to insulate piping, and there are different insulation products and systems out there, but probably the one that is most commonly used in light commercial would be an elastomeric foam. And you can buy this in tubes or coils or sheets, and it's actually pretty easy to work with. Over in the lower right there, I'd like to see neatly installed insulation, and to do that, it takes a little time to cut the miter joints and glue it together properly. You don't want to leave the joints just butted together. Over time, it will shrink and it'll pull apart, and you'll get condensation forming. So the key idea is not to let the surrounding air get to any metal or plastic, for that matter, that's carrying chilled water. And a little installation tip, one of the things I found in working with this, an electric carving knife really does a good job of cutting this material. It's definitely easier to work with than like a utility knife would be. It doesn't tend to tear the material. So maybe if you can go in the kitchen and just borrow that carving knife, or splurge and buy yourself a carving knife and put it in your toolbox, that works pretty good for cutting these miter joints. This is a table actually came out of, I believe it was the Hydronics number 27 or number 30. And it shows different insulation thicknesses of elastomeric foam that would prevent condensation depending on the chill water temperature and also what kind of dry bulb and relative humidity. I'll cut to the quick. 1/2-inch elastomeric foam will stop condensation in just about any typical application. I mean, if you're in a sauna with extreme humidity and you're working with 35-degree fluid, you might want to go to a thicker insulation, maybe 3/4 inch, but 1/2-inch elastomeric foam works pretty good. Also, I'll put a plug in for this. We used these on a recent project, and I was really impressed. The Hydronic company makes these. They're just plastic clips that go into a channel strut. But if you look at that copper pipe, you'll see inside that clip, there's actually little ribs that mechanically support the pipe and keep it concentric with the outer ring, and that allows you to slide this insulation right in. And what you don't see here, the final step would be to take a silicone caulk and just put a nice fillet where that insulation comes into that clip. So you've got basically an airtight seal there, and you're not going to get condensation. So it's a lot better than trying to insulate the pipe and then just put some kind of a simple hanger underneath it. Over time, the insulation will sag on the hanger. It doesn't look very good. This is a system that prevents that sag. If you're insulating around zone valves, don't insulate the actuator. You see the valve body is insulated here. One of the things that I'm kind of on a crusade for right now is trying to get more pump manufacturers to offer these insulation shells as we move into systems with heat pumps, and this potential for chill water cooling in smaller scale buildings is certainly going up. We need to be able to insulate the circulators. This Grundfos Alpha product, you can buy an insulation shell. One of the things I will stress, it is not sufficient just to put the shell and just push the two halves together. You need to seal it up completely with either foam tape or caulk. You cannot let surrounding air get inside that shell and get to that volute. If it does, it's going to cause condensation. So we'd love to see more insulation shells products on the market, not only for circulators, but for isolation valves or other components, so that it's easier for an installer to create a good monolithic insulation system on their piping. Now, domestic water is another possibility, and I'm just showing a reverse indirect tank here, basically in parallel with the circulator and the high mass distribution system. And some of the heat pumps today do have the controls where you can call for domestic water heating separate from space heating. And all that does is allow the heat pump to target a higher temperature. And I put down, yes, this is a possibility, but you want to evaluate the domestic water needs in the facility. What we have found in many of these garage facilities is that there really isn't much demand for domestic hot water. They aren't really washing the equipment inside with hot water. Some of them might have a shower, others no shower, just a couple lavatories. When you have minimal need for domestic hot water, this may not be cost effective to do this, as opposed to either a tankless electric water heater or a small tank type water heater. So I'm showing it as a possibility, but evaluate, is there enough domestic hot water demand to justify the cost of doing this? Now, here's a kind of, I'll call it a bit of a futuristic concept. What this is, if we look at this cross section up here, you'll see there's a heated slab and there's insulation. This light blue material would be insulation. But down below that is another larger area, and we call that a solid thermal mass. And the idea here is that we have tubing. We have, perhaps I'm showing 2 grids of tubing installed in this thermal mass. I can't tell you, is that optimal? Do we need 3? Do we need 1? That would be where computer simulation comes in to evaluate this. But the concept is we could run the heat pump perhaps during off-peak hours, add heat to this thermal mass, and then when we need that heat, we could bring it to the upper slab. And the reason I'm putting insulation between the upper slab and the lower slab is we have thermal separation. if we don't have that insulation there and we drive this thermal mass up to an elevated temperature, we could have overheating, and we have no way to control that. But with a layer of insulation in between, you know, we could do things like just close the zone valve or shut off the circulator, so we aren't allowing the heat that's stored in the solid thermal mass to just keep flowing up through that upper floor. I wanted to put this in as just, as I say, a concept drawing, and you know, thinking about what are some of the materials that could be used. One thing that probably comes to mind, but I'm going to caution you, is sand. Sand is really not that good as a conductor. So the problem with sand is you have, if you think of it microscopically, you have a lot of point-to-point contact with those granules of sand, and that's not good for heat transfer. That air in between is inhibiting heat transfer. But there are materials on the market now. They're generically called flowable fill, and basically what they are is a very low strength mixture of Portland cement, sand. In some cases, there's fly ash added to it, and it's mixed up to be quite, I want to say, think of it a milkshake consistency. And you can see the photo in the bottom there. Very flowable fills are used for filling excavations, for example, a road cut where a culvert pipe would be put in, rather than put multiple layers of soil in there, compacting as they go. In some projects, the engineers will specify flowable fill. It's actually material that an excavator can dig out. It runs between 80 and 100 pounds per square inch compressive stress. It is strong enough to support the slab above it without any problems. But it's because there is cement mixed in with the sand, you have better thermal properties. And I'm currently looking into this, trying to get good solid information on these materials so we could do some types of simulations. But I wanted to show the concept to you. Again, this is trying to move away from very expensive multiple 1,000-gallon tanks of water into something that is much less expensive and logistically easier to incorporate into a project. So flowable fill is one possibility here. There may be other materials. Solid concrete would work, but it's quite expensive. So we're looking for something that has respectable thermal properties, but is definitely less expensive than solid concrete. So our final poll question. As we've gone through these slides, I've talked about different utility rate structures, time of use electrical rates. Could you currently use time of use electrical rates from your local utility company to save money in operating costs? So I'll let Max run that poll. And as he's running that, I'll just mention more and more electric utilities are getting more creative in terms of trying to do their peak shaving. So we're going to see more possibilities for not only time of use rates, but real-time electric pricing and so forth. So again, I look at how can we, as hydronic heating professionals, working with heat pumps, working with thermal mass, how can we coordinate with these rate structures to not only help the utilities, achieve what they want to do, but also bring our total operating cost and our demand, our peak demand down. So let's see. I'll let Max run that.
Okay, so it looks like the votes are starting to trail off here. So let me share that. So we had, could you currently use time of use? We had a 56% yes result there. So yeah, like you're saying, John, I know that the heat pump water heaters, the manufacturers are all working towards a shared communication network, basically called an EcoPort, that would allow for real-time communication with the utility companies to respond to what's happening in the grid, not just to schedule, okay, turn it on at 6 p.m. because that's when the rate's better, but to be pretty dynamic. So that technology is coming with the policy support and then manufacturer support that could work just as well for an air-to-water heat pump.
Yeah, Yeah, so we're actually I feel the hydronics market, concepts like this, we have the materials and we have developing design concepts that really would coordinate well with where these utility rates are going. It's a good time to be in the hydronics industry. Okay, so Max, I'll let you run through these final slides.
Sure. So if you have any questions that come up about a product or a system, give us a call. We can walk you through, is this installed backwards all the way through? Is this a good selection for a balancing project? Let us know. Those are some of the people on the team that will answer the phone when you give us a call. We have the Ask Caleffi podcast is a great thing to listen to if you're on the way to a job site. This was kind of designed with contractors in mind, with two former contractor hosts, Greg and Dan, to talk you through, really calls that they're getting on the phone lines to see, this is coming up a lot. Here's a good A, B, and C choice if you're ever faced with that. And then Cody Mack has done this video series for us. If you're a distributor, this is one of the things that I like to point people towards all the time. These are kind of like Coffee with Caleffis, but in a 5 to 7 minute segment. So we know that that's realistic for someone who's at the counter who may not have the time to sit down for an hour without being interrupted in the middle of the day. That can be a nice little recap series for people that just have a few minutes and want to brush up on something. And then follow us and tag us on all these social platforms. If we see a cool job site and we're tagged, we love to reshare that for you to kind of boost the visibility of jobs that you're proud of. That's something that's always fun for us to see what you're up to and what creative projects that you're involved with. And honestly, it goes into product development as well. If we see everybody has started using this valve like this, maybe we should look into that a little bit further. That's kind of the best real-time feedback we can get anymore with social media. And then happy Thanksgiving, happy belated Thanksgiving, I guess, for the Canadians on the call for next week. And then we are going to have the one more Coffee with Caleffi this year in December 15th, and then we'll take a little bit of a break. And we're going to come back with John in February and March are going to be a two-part series that is going to correlate to our next issue of Hydronics, which will be released at the AHR show in February. And that's going to be on hydronic troubleshooting. So that should be a really nice, print copy, digital copy, Hydronics copy that will have John kind of walk us through with some things that he's learned over his years in the industry that'll be really useful. So that takes us to the end of the slides. We got a lot of questions, pre-submitted questions, as well as during the webinar here. So one of the things that that came up a couple times too is piping materials that you mentioned. If you're going to insulate, I'll say that a lot of the, if you were saying copper versus a polymer, a CPVC or a PEX or a PPR, you still have to insulate. I know that sometimes those polymer companies will advertise that they have a little bit of an insulation value, would not be enough to cover kind of the systems that we're talking about.
Typically, it's not enough. If you're dealing with fluids down in that 40, 45 degree Fahrenheit range, they're correct that the plastic tube does have more thermal resistance. You're still going to get condensation. So you might be able to go with a slightly thinner wall. You'd have to, evaluate that. But the idea that you can eliminate insulation on a chilled water system if you're using plastic pipe, I would not suggest that at all.
And then we have some other questions come in generally about, air to water heat pumps versus a geo-exchange system where you're putting pipe in the ground. What are some ways that you would kind of evaluate, should I do one or the other if you're looking at a new project? And you've covered this a little bit, but we got a bunch of questions about that.
Yeah, well, certainly I'd start with the site. Do you have a land area, for example, for a horizontal earth loop? Rural areas might, larger lot sizes might have that area. Is it going to disrupt any existing underground utilities? If it's a retrofit, things like driveways, septic, water, water mains. If it doesn't have the land area, you may have to go to a vertical borehole system. They tend to get pretty expensive these days. In my area that it runs right now, about $3,500 per ton to drill a borehole, put the pipe in and grout it, and additional money to connect the multiple boreholes together and bring them back in. So residential systems can easily be into earth loop costs $12,000 to $15,000. Now, there are 30% tax credits that actually goes to the Inflation Reduction Act, changed where the phase out and what the percentages were in residential projects. 30% is in place for the next 10 years. So the geothermal heat pump industry really made out well with that. The other thing that I would tell you to look at is return on investment. The COP of the geothermal heat pump is probably, if it's a well-designed system, is probably going to be a little bit higher than an air to water, but not crazy higher. It's not going to be twice as high. It might be 10 to 25% higher, something in that range, but with substantial additional costs. So I always stress, you don't pay for COP. Don't get hung up just comparing, heat pump A with its COP value to heat pump B with its COP value. Look at kilowatt hours, and return on investment of air to water versus geo is, even without air to water, subsidized. And there are a couple states right now, Vermont and Massachusetts, that do subsidize air to water heat pump installations. I think we'll see more states do that. But even unsubsidized, you can still make a pretty good case of air to water versus geothermal where things are. And certainly if we eventually reach a point where we don't have subsidies on geothermal heat pumps, I think even stronger case return on investment for the air to water. And by the way, I'm not against geothermal heat pumps. We've designed them over the years. They work well, but typically in a retrofit situation, the logistics of dealing with a properly installed geothermal system just are much more challenging than setting a unit outside on a pad and bringing a couple pipes into the building.
One of the things that in a new construction setting that is kind of interesting to look at for GeoExchange is if you are drilling a hole already for some really deep structural pilings, if it's going to be a larger building, that can be a great spot to just put the pipe into the ground in those structural pilings. It's something that you have to work with the structural engineer, but it's not like a little bit of PEX down in that hole is going to make the building unsound. And that is a way to kind of meet in the middle, that you're not even paying to drill a new hole, it's already there. So you might be able to jump on that. Again, kind of a niche within a niche in this conversation, but that could be an option.
A cut fill operation on site grading is another possibility. If you're moving substantial amount of dirt around, you might be able to coordinate that with placement of the earth loop. But again, those are kind of specialty cases. The general case where you're just going to either do boreholes or get a big excavator, it's very disruptive. Again, we've done it, it works, but as I say, going back to looking at a broad market, looking at the potential to bring a heat pump into, especially in a retrofit situation, I think air to water holds a lot better logistic advantage over a geothermal than right now. Today, again, we have a very heavily subsidized technology competing against an unsubsidized technology. So that does skew those numbers a bit, but even with those differences, we're still seeing good return on investment with the air to water.
And then a couple of questions that they're probably more heat pump manufacturer questions as well, would be kind of related to, well, what about having glycol out to a monoblock versus a split system? What's the most efficient way to do that? And I think it's a little bit of a balancing act between the installed cost
Yeah,
and
they both have their pros and cons, Max. I mean, the nice thing about a split system is you don't have to use antifreeze. That's probably the biggest advantage. The downside is you do need some basic refrigerant skills and tools to install it. You have to install the line set, pressure test it with nitrogen, pull the vacuum, release the refrigerant that's in the outdoor unit. It's not complicated, but it is a skill set and perhaps a tool set that the average plumbing and heating, plumbing contractors typically don't have that skill set or those tools. If it's a company that does do HVAC and they do, for example, air conditioning systems, they very likely do have those tools. So there's a trade-off there. The downside with the monoblocks is you have to have antifreeze. Most of the manufacturers will not warrant the heat pump if it's just water. There are a couple design options. One is use antifreeze throughout the entire system. The other option would be to put a heat exchanger in between the heat pump and the balance of the system and just use glycol between the heat exchanger and the heat pump. And we've looked at both of those. Again, there's trade-offs. You use less glycol, certainly, if the heat exchanger is there, but you do impose a performance penalty on the heat pump because you have to have a temperature difference to drive the heat through the heat exchanger at whatever rate the heat pump is producing it. And that can back the operating temperature of the heat pump up easily 5 to 10 degrees Fahrenheit. And if we look at those curves on performance, it will definitely have an effect on seasonal performance of the heat pump. So I was originally kind of leaning towards the camp of putting the heat exchanger in there, but from a performance standpoint, putting antifreeze throughout the entire system really does give you the better performance. Again, you would have to evaluate the cost of putting the heat exchanger as well as another expansion tank, another circulator, and some safety controls because you're creating an isolated pressurized loop now between the heat exchanger and the heat pump. Evaluate that cost versus the antifreeze cost. I tend to lean towards just using antifreeze throughout the system at this point and actually selling that as an advantage because in a prolonged power outage, the entire system would be protected against freezing.
one of the kind of funny asides with this for this application too is that if this is like I know my dad had worked on a diesel mechanic shop. The employees really like it. They don't want to leave that job and go work on a cold slab again down the street for an extra $5 an hour. So I don't know how to monetize that as part of your bid package, but it's
Sure.
just a little bit nicer creature comfort for people that sometimes are on the floor all the time under the trucks and things like this in this application.
Absolutely.
So
It's a
let's see,
great.
any other questions that the other Caleffi team members see that we should grab while John is still here live? We'll follow up with, we've got a mountain of them, so we'll follow up after the webinar with some of them that are a little bit more specific.
Yeah, hey there, Max and John. We have one question in here, one kind of comment regarding using air to water heat pumps along with solar thermal for those places where they do get a lot of solar or a lot of capability to get some solar thermal energy. What are your thoughts on that, John? I mean, as far as getting that integrated into a system like that?
Yeah, certainly it could be done. That the last slide. Let me just see if I can go back to it here. The slide that showed that extended thermal mass idea, certainly solar collectors could be used when there's solar energy available to inject heat into that solid thermal mass. The challenge with solar is you can't control when it's available. So you have it or you don't have it, and where do you park it when your building doesn't need heat but you have solar gains? So traditionally it's been done with thermal storage tanks, but for space heating, again, we get into the challenge of those tanks have to be very large, and as such, they're very expensive. So going back to a solid thermal mass with solar input, yeah, I don't see any reason why that can't be done.
Yep, definitely some considerations there, that's for sure. So appreciate the input there.
Mhm.
I think that was about it for me, Max. I don't know if you saw any more of them in there. I think you hit all the good ones there too. And anybody else, obviously, we'll make sure to get to any questions that you had. If there were really more intricate or detailed questions, those might be something for offline as well. So.
Yeah, I think those are the ones that are kind of most applicable to the whole group here. So yeah, thank you again, John. We'll have one more coffee with Caleffi in December. Then we'll take a break for January. We'll be at the AHR Expo in Atlanta, and then we'll be back in February with John again to cover troubleshooting.
Thank you, Max
All right.
and Cody.
Thanks,
Yeah,
John.
thank you. All right, thanks everybody.